Good afternoon. Today we're going to talk about wave interference. Interference is something that does not really happen with things like particles, which we've been studying for most of the year. For instance, if I have these two ping pong balls, this one says speedster, this one says integra, and I have them collide, they just bounce back off each other. We know that nothing weird like they pass through them happened because this one is still speedster, this one is still integra. Okay, particles just kind of bounce off each other. Nothing fancy happens. Waves, on the other hand, do some weird stuff. When waves are on a collision course, they actually pass through each other. So, for instance, here's a couple of wave pulses. One is heading in this direction, one is heading in this direction. After they pass through, here's what they look like. We know that they must have passed through each other because this wave is now on the left-hand side of this wave is now on the right-hand side. They've essentially swapped places, okay? But that happened because they simply passed through one another. Particles don't do this, okay? If you throw two basketballs at each other, they don't pass through each other, they just bounce off each other. Not only do waves pass through each other, different from particles, but they also interact while passing through each other according to something called the principle of superposition. What this means is that the displacement of the combined wave from the equilibrium position is equal to the sum of the displacements of each individual wave. Essentially, this is interference. Okay? So this line right here is a little confusing. The displacement of the combined wave, when the waves are overlapped, the shape of the wave you can find by simply adding together the shapes of each individual wave before they were overlapped. Now, we're going to have a lot of space for examples down here, so right now, just to prep, why don't we split this into 3 sections. But before we get to that, we're going to look at a simulation. We've done this simulation before. It's waves on a string. And what I'm going to do is I'm going to create a wave pulse. Oh, that's not what I want. Hold on. Let's get rid of that one. All right. I need no damping. I need high tension. Pulse. Slow motion. I want the pulse width to be narrow. I want the pulse width to be, or height to be high. And let's do a loose end for right now. So I have my first pulse. Now, at the loose end, it's going to reflect back the same way. And I'm going to create another pulse. And I want you to take a guess as to what's going to happen when they're fully overlapped. You can already see something strange starting to happen. This wave right now is this high. This wave is this high. When they combine, watch what happens. Twice as high as either individual wave, all the way up here. And okay, so pretty close to the top bar here. And if I let them go, now they're back. So those waves were up here. It was like twice the height. Now, that wave is going to flip. What do you think is going to happen this time? This wave has an amplitude up here. This wave has an amplitude down here. When they combine, it looks like they should just about cancel each other out. And that's indeed what happens. I'm going to have to let that run for a little bit, just so we see that again. So these waves are going to cause a big wave down here. And then the combined wave, when it's opposite, almost perfectly cancels out right in the middle. And again, we predicted that by basically looking at the shapes of the waves, and we can kind of like add them together in our head if they're very easy, if they're nice and simple pictures like this. And we know that they pass through one another because initially this wave was over on the left-hand side, this wave was over on the right-hand side. Now they've swapped places. Now I'm going to show you just one more with this. Okay, so let's see. Let's do that, and then let's do a pulse. Let's do about half the height or so. Okay. So this time, again, They should build, they should be taller, but not quite as tall as they were before when it was two similar waves. All right, definitely bigger than one wave, all the way up to about the top of the pole. And they flip. Now down here, we should get a wave that is about, let's see, maybe about half the height, but down below. And that is exactly what we get when they're superposed, when they are overlapping. Okay, and again, this is all just waves interfering with one another. So the basic principle is pretty straightforward. Let's say that you have waves that look like this. You have a couple of square pulses. You get a square pulse like this, and a square pulse that's a little bit bigger over here, like this. This one's traveling this way, this one's traveling this way, and let's say we got 5 centimeters and 7 centimeters. When they are combined in the middle, you're going to get the sum, you're going to get a bigger pulse right in the middle, and you're going to get something that is the sum of these two heights. So you're going to get 5 plus 7 is 12, going to look approximately like this. Okay, notice the width didn't change, but this is what it looks like when they're overlapped. Once they've passed through each other, the waves continue on their merry way. Okay, they pass through each other as if nothing had happened. This will also work if we have curves. This is kind of our first example that we did. So let's say this is 4 centimeters. This is also 4 centimeters. I guess you could say negative 4 centimeters. That's heading this way. That's heading this way. These waves, when combined, are actually going to perfectly cancel each other out. But after they're done, they'll go back to normal. You could even have something a little bit more complex that looks like this. Let's say this is 10 centimeters, and it's heading this way, and this isn't going to be the same shape, it's instead going to be a divot kind of shape like this. And they're heading towards one another. We want to know what happens in the middle. Well, what I like to do for this is I kind of draw dotted lines for what the wave shapes would be. So here would be the square. Here would be the triangle part. And then we simply just add up the shapes at each point and see what would happen. At the left edge of both of these, it's when they're fully overlapped, they're both at 0. Or actually, this one's up at 10, this one's at 0. So we know that the wave at least starts up here. This wave continues across flat. This wave starts to go down. So let's say that right here, this is at like negative 1 centimeters. This is up at 10. We add together 10 and negative 1, we get 9 centimeters. So that one starts to go down. And that's going to be true all the way down to the middle, where this one at the very middle is at negative 10, and this one is at positive 10, completely canceling each other out. They build back up on the other side. The wave shape ends up looking something like this, right in the middle. Okay. Obviously, the dotted lines wouldn't really be there. That would be the shape that you would see. Once they're done passing through each other, they then again look as they did. So the waves themselves aren't affected by passing through each other. The only effect is noticed when they are perfectly overlapped, or actually when they're overlapped at all, but the biggest effect happens when they're perfectly overlapped. Here's another example. This is actually an AP question. This is right from the AP, my first year that I was teaching. It's the same principle. If you and your class did this, this was like an easy 7 points on the AP exam, which is a lot of points. All we have to do is we think about where these are going to be combined, and we kind of imagine how big each wave is at that point. So I think, let's see, these waves are 3 boxes long. Okay, they move 1 unit per second. So if I do this right, I think they start to overlap. So let's see, 1, 2, 3, 4, 5. I think it's right here. 1, 2, 3, 4. Okay, yeah, so they overlap when the left edge of this wave gets here, the right edge of this wave gets here. This wave up above goes up 2, and then it goes down 1, and then it goes down here. It's 3 wide. This wave goes down, let's see, it goes down 2 at first. So that'll be down. So that first wave looks like this. This wave goes down 2 and then goes down another 2 and then shoots back up to the top. So at this point, at the left edge and the right edge of both waves, they're both at 0. So they both start here. 1 unit over from the left edge of both waves. This wave is up at 2 centimeters. This wave pulse is down at -2. So they totally cancel out. We get 0. At 2 units to the right from the left edge, this wave is at +1 centimeter. This wave is at -4 centimeters. Add those together, 1 plus a -4 gives us -3. So the wave shape ends up looking like this. Okay, that's what you would get when the waves are totally overlapped. And I realize I should have drawn it down here. Not a big deal. Okay, so that's interference in a nutshell. You're mainly going to have to be able, not necessarily to draw these, but to understand what should happen if given a situation like this or like this. These are the two that you really need to know, basics. Sometimes you might get a question that looks sort of like this. Okay, a couple more things to talk about on the front here. Constructive interference. Constructive interference occurs when 2 interfering waves have displacements in the same direction, such as this example. Okay, their displacements are both positive. When waves are perfectly in phase, meaning they're perfectly overlapped, allowing the crests and the troughs to align in both locations, then there is what's known as maximum constructive interference. And this is maximum constructive interference is more for periodic waves, okay? Waves that repeat over time, such that the crests and the troughs are both perfectly lined up. With pulses, it's just, okay, they have constructive interference at this point. So an example would be a section of a periodic wave that looks like this. We add to that, let's say it's moving in that direction, we add to that a section of a periodic wave that looks like this, going in this direction. When they are completely overlapped, that will mean the left edge and the left edge are lined up, the right edge and the right edge are lined up. We're going to have 2 crests on top of each other, 2 troughs on top of each other. It'll look something like this. Okay? When perfectly overlapped. You see that they build on each other to make a bigger wave. It doesn't stay that way, but when they're perfectly overlapped, that's what happens. Destructive interference is the opposite. When 2 interfering waves have displacements in opposite directions. When the waves are perfectly out of phase, 180 degrees, or in other words, separated by 1 wavelength, or 1/2 wavelength, I should say. The crests are aligned with the troughs. There is what's known as maximum destructive interference. And that cancels out the wave during the overlap. Not permanently, but while they are overlapped. So this is destructive interference, then this right here is maximum destructive interference when it perfectly cancels out. This is destructive interference as well because it lowers the, it doesn't make the wave bigger, it makes the wave actually a little bit smaller. Another example would be, let's say you have, again, this sort of shape moving this way, plus this shape, and it's moving this direction. When the left edges line up and the right edges line up, you're going to get this. It completely flat lines because this crest will be lined up with this trough will be lined up with this crest. They'll completely cancel each other out only when perfectly overlapped. It's not permanent. Once the waves aren't perfectly overlapped anymore, once they continue moving, or as they continue moving, you'll get the wave shapes back again. All right. Let's talk a little bit about how this can happen with sound waves, because this is very important for designing things such as concert halls and how you're going to hear music. Okay, so what I have here are 2 speakers and this guy, and we're going to play this, and I think you should hear. something. Okay, you hear something. So right now, this guy is hearing this sound. As I move him around, you'll notice that the sound gets louder and softer. If I move him farther away, it gets softer. If I move him towards, typically it gets louder. But that's not the whole story. Look at this. It's actually, if I move him a little bit to the side, there's almost no sound right there. It's very, very quiet. And he's right in front of one of the speakers. Watch what happens if I move him back a little bit. It's much louder again. Matter of fact, there's a spot I could put him that's like right in front of one of the speakers, and you can barely hear anything. Whereas if I move him back, it gets louder. Something weird's going on there, and it has to do with constructive and destructive interference. Okay, let's turn that off. So, here's the two speakers, A and B. They are emitting sound waves in phase with each other. They will produce what's known as an interference pattern. Hopefully you can see the little white and black diamonds that are on this page. Notice, and let's assume, for our sake, that the crests are the dark lines, the troughs are the dashed lines. Notice that wherever a crest and a crest happen, there's a black triangle, or a black diamond. Wherever a trough and a trough line up, that's also a black diamond. Those are areas of maximum constructive interference. The black marks represent where two crests or two troughs come together, and where there is maximum constructive interference. That means the waves overlap and build on each other to make a louder sound. The white marks, on the other hand, show where a crest and a trough overlap, causing maximum destructive interference. Anywhere there's a black mark, what ends up happening is the difference in path lengths from each speaker is equal to an even number of half wavelengths. So 2 half wavelengths, which really means 1 wavelength, or 4 half wavelengths, which means 2 full wavelengths, or 0 half wavelengths, which means the exact same number. Basically, if you think about it, so like this black mark right here is 1 wavelength from A, and it's 2 wavelengths from B, which means that the phase difference is 0. Those waves are in phase. This black mark is, let's see, 1.5 wavelengths from B and 2.5 wavelengths from A. That means that the phase difference is 0 because there's 1 full wavelength in between, of distance in between. We have both troughs. And also, I just want to point out, 2 troughs does not mean destructive interference. That's still constructive because it's 2 waves that are in phase with each other. On the other hand, the white marks, so like this one, is 1 full wavelength from A, 1.5 from B. The length difference is 1/2 of a wavelength. The waves here are exactly out of phase. White marks represent places where the difference in path lengths is equal to an odd number of half wavelengths. So what's happening here is that the louder sounds occur where there is maximum constructive interference, where the path difference is equal to an even number of half wavelengths. The quiet spots, the dead spots, are where there is destructive interference, maximum destructive interference, because the path difference is equal to an odd number of half wavelengths. Basically, the waves that are reaching that point are out of phase, exactly out of phase by 180 degrees. So you have like a crest and a trough over the top of each other, they cancel out. This is really important when designing things like concert halls and auditoriums, because you don't want there to be dead spots. This is why it's not good to have concerts in like a gymnasium. Gymnasiums aren't designed for maximum sound, to eliminate dead spots, in other words. The sound's not going to sound as good in a gym. Okay, last thing that we're going to talk about today are standing waves. Standing waves are created if you have 2 waves that have equal amplitudes and equal frequencies, and they travel in opposite directions in the same medium. Once they overlap, it produces an effect known as a standing wave. It's called this because if you view the wave, it doesn't look like the wave is moving one direction or the other, because those 2 waves that are overlapping are combining in such a way that it doesn't look like it's moving. This right here is an example of a standing wave as time goes on. You can see that we have two waves. We have one wave that's moving this way, we have one wave that's moving this way. When they're perfectly overlapped, they create this big wave right here. Once those two waves start to move apart from one another, however, that wave kind of decreases. And as they continue to move apart, we start to see some destructive interference. This is maximum constructive interference here. This is destructive interference. But you can't get standing waves from just looking at a picture. You have to look at this app. This is a phenomenal app for showing this. So right now, and I've showed you this before, we have a wave showed by these blue tick marks that's moving to the right. I can also show this orange wave that is moving to the left. It has the same amplitude and both waves have the same frequency. If I turn them both on at once and go to slow motion, and I pause it right there, those waves are perfectly in sync. This is constructive interference. They're perfectly aligned. The crests and troughs are aligned. If I let it go for a little while, now these waves are basically in perfectly destructive interference. The crest of the blue is aligned with the trough of the orange. Crest of the orange is aligned with the trough of the blue. But they're going to keep alternating between perfectly aligned and perfectly unaligned, maximum constructive and destructive interference. I can also turn on this green wave, which is the superposition, the combination of both waves. Right now, when everything's aligned, we get this overall wave that looks like this. Once they go to destructive interference, look, that wave's almost completely canceled out. If I do this in real time, we get this wave that does not seem to travel. If I turn off the blue and the orange, you can't tell what direction this superposed wave is moving in because it's not really moving in any direction. And if you make it move fast enough, where's my mouse? There it is. Make it move fast enough, and this isn't a great option, but it almost looks like they're just forming loops on the screen. So, I'm going to show you another example of that in just a little bit. That's what standing waves look like. They oscillate in patterns between this line here and this dotted line here. Okay? And so you can see that they oscillate between, so if you look, sometimes it looks like this, and then it oscillates to this. A standing wave in real life would look like this. We can actually show this with waves on a string. Okay, I'm going to zoom in a little bit. And what this guy is doing is he's got a wave generator. Now, if you look right here, there's actually a little motor that is pumping the string up and down. That's what's causing this wave. And if you look, it looks kind of like there's one loop of this wave. If I fast forward a little bit, he's fiddling around with it. He's turning up the frequency in such a way that he's going to get two different loops. So you can see that there's two different loops on the string, one right here and one right here. If we fast forward a little bit more, he's now got three different loops in his wave by turning up the frequency. You guys don't have to know too much about that, but I want you to see what a standing wave looks like. If it's oscillating fast enough, it looks like it's not even one string. It looks like you've got two strings on there. Like right now, of course, when I pause it, it looks like there's four different loops on the string. Here, 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 and here. By the way, notice that this is a fixed end. What's actually happening is there's a wave the wave that's getting generated over here by the motor is getting reflected by this fixed end, and that's what's causing the standing wave. 5 loops, 1, 2, 3, 4, 5. Now, we've got to talk a little bit about the features of these loops. Any location, so we're alternating between these two states. Any location where the lines meet, here, 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 and here, is a part of the wave that, due to permanent maximum destructive interference, never changes its displacement. This is known as a node. There's other places where there are peaks, like, so here's a node, here's a node, here's a node, and here's a node. There's other places, like here, this like area, okay, this spot on the line, where there are peaks. These are areas of maximum constructive interference, and they're referred to creatively as antinodes. Okay, so on this video, where we get this looping here, this area right here where it seems like the wave isn't moving, We have a node and a node and a node and a node and even a node over here. And the loops, okay, the centers of the loops are known as antinodes. So we've got antinode, 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 another antinode, and then node, 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 node. And there's supposed to be a node right over here, but you can't really see it. We can also see that on our simulation here. If we do this in slow motion, look, there's some spots here and here and here, 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 and here, where it doesn't seem like the wave ever leaves this equilibrium line. On the other hand, there's spots here, 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 here. Basically, it looks like every 4 lines or so where there is an antinode, where we get those peaks and those valleys, okay? So the antinodes are where you get the loops. The nodes are basically what kind of constrains the loops, okay? And again, the way that one standing wave got created that we saw was it got created by reflection at a fixed boundary. And then very quickly, because we're going to talk about this again in the next video, the reason that standing waves are so important is because it's a feature of resonance. Standing waves have interesting effects if they're allowed to interact over long periods of time. Every object has what is known as a natural frequency. Objects have these natural frequencies. They're the frequencies that an object will tend to vibrate at. Natural frequency, singular. It's a frequency that an object will tend to vibrate at if you hit it or something like that. Will vibrate if it is disturbed. If a wave with the same frequency as the natural frequency of the object interacts with it, it will actually cause the object to start vibrating all by itself. This is the trick. Well, first of all, this is known as resonance. This is the trick that, let's say, an opera singer uses to break a glass with their voice. They sing at the same frequency as the natural frequency of the glass. Basically, what happens is the glass molecules, the atoms, start to vibrate back and forth, and they actually break the glass. Because they start vibrating back and forth enough, they have enough energy, the glass actually shatters. This is also the trick behind doing the old wine glass trick, where you have your finger and it has some water on it, and you rub the edge of the glass and with the water in it, and you get a sound out of it. Resonance is also the principle behind every single musical instrument ever created. Once you get resonance set up, it actually increases the volume by like 10 times. And, I already mentioned this. It's a phenomenon that lets an opera singer shatter a glass with their voice. We'll talk more about the examples of resonance in a little bit, but let me just mention musical instruments. Every musical instrument it works because of resonance. Standing waves get set up in the instrument, and it causes the tone that they produce, the frequency of the waves, to be amplified so you can actually hear it. That's why wind instruments have these big air chambers. It's why drums are designed the way they are, and it's why violins and cellos and guitars are designed the way they are to maximize the effects of resonance. Okay, that's a lot about interfering waves. So we covered constructive and destructive interference. We covered how to determine what the wave shape will be. We covered standing waves, and we covered resonance. We'll talk about sound waves specifically in our next video.